Hello and welcome to the lecture on 6.1. Today we're going to talk about trigonometric functions and right triangles. I don't like the order in which the book writes these out. I think trigonometric functions and right triangles should actually be before the unit circle, so we're going to cover it in that way. But if you wanted to see the unit circle first, then go on a couple of sections down and you'll see 5.1. That's where we start the unit circle and trigonometric functions in the unit circle. All right, here we're going to start with quite a few definitions. An angle, AOB, consists of two rays, R1, which will be equal to OA, and R2, which is equal to OB, with a common vertex O. So what this will look like will be here. We have one ray, and we have a second ray. Call this R1. We would have O being our vertex, where it's at the corner of the angle. That means that this point would have to be A, because we have R1 is OA, so this ray. And then R2 would be here, and this would be B. R1 is called the initial side, and R2 is called the terminal side. Now what this means is that we're going to end up rotating from R1 to R2, and we're going to get into that definition in a second. So we start here, our angle starts here on this side, which is the initial side, and it ends here on the terminal side. And it does matter. You might think it doesn't matter because what does it matter if we start here and end here, or start here and end here? We would have the same angle, right? That's actually wrong. We'll get into that in a second. If the rotation from the initial side to the terminal side is counterclockwise, then the angle is positive. If the rotation is clockwise, then the angle is negative. And that's what I meant when I said that these are not the same angle, depending on what the initial side and terminal side are. So if this is the initial side, and this is the terminal side, how I've drawn it, then rotating from this side, R1 to R2, gives us a positive angle, but rotating from R2 to R1, which would mean then that R2 is the initial side and R1 is the terminal side because we start here. If we rotate from R2 to R1, then it's negative because we're rotating clockwise. The absolute values of the angles are absolutely the same, but this is important. This is an important concept. And here, if we're rotating from R1 to R2, then clearly we're moving counterclockwise, so we have a positive angle. And similarly, here, if we're rotating from R1 to R2, we're rotating clockwise, so we have a negative angle. You'll want to get the terminology about clockwise and counterclockwise directions down, and you'll want to start using that as early as possible in this course. What you don't want to say is that we're rotating up or we're rotating down. That doesn't make sense. The reason that doesn't make sense is because suppose that we had an angle in this way and you were using the terminology up or down. We're rotating here. Now, if you were still using that terminology, rotating up or down, we would say that this is rotating down. So it would be negative, right? But you would be wrong. This is still counterclockwise direction. We're going in this direction, which is counterclockwise. So we have a positive angle, right? So it's important to understand that when we talk about rotation, we use clockwise and counterclockwise for our terminology. The measure of an angle is the amount of rotation about the vertex required to move from R1 to R2. So if we had R1 here, and we're rotating counterclockwise to R2, we would have a positive angle, sure. But how much? What is the amount of rotation that we actually did? That's this distance here. Depending on what units we use, and we'll get into those next. So we have two different measures. A degree is 1 360th of one complete revolution about the vertex. Now, this unit of measure is one that we should all be pretty familiar with. 360 degrees is a full revolution. 180 degrees would be a half revolution, be like turning around. And then you have the 45 degrees and all that stuff. And we'll go into those a little bit more later on. Next, we're going to talk about radians. This one's a little bit less ubiquitous. If a circle of radius 1 is drawn with the vertex of an angle at its center, then the measure of the angle in radians, rads for short, is the length of the arc that subtends the angle. What I mean here, let's draw a circle first. We have an angle at its center. So here's our angle. Let's R1, R2, and we get this. Now, what I mean when we say we subtend the angle, it's going to be the length of this part of the circle. This arc subtends this angle. Now, the reason that we say radius 1, that we have a circle of radius 1, is so that we can use this length here, the actual length, as a measure for the angle. Now, when we talk about radians in the future, we no longer care if the radius is 1, we just say that we are 1 radius length around the circle. Let me show you what I mean here. So each circle has a parameter, r. R is the length of this radius. It's a descriptor. It tells you how wide the circle is. Right, now, if we take this radius, this length here, and we bend it a little bit so that we can fit on the arc, we'll get something about here. We would say that this is 1 radian around the circle, because we took 1 radius and we went that distance around the circle. Now here in the definition, we have a radius of 1, so the length is equal to the amount of rotation that we have in radians, though. So if we did 2 radians, we would have something that looks more like this. This would be about 2 radians. So right about here. So we take this length, and we would go about this distance. This would be 1 radian, because we took 1 radius length, and then we take a second radius length, and we go this distance here. This would be the second radian, so this distance is 2 radians. As many of you probably know, there is a ratio that we use, a number, that is very interconnected with circles, specifically pi. Pi is exactly 180 degrees. It is the same thing as going halfway around a circle. So this distance is pi radians. Now you might notice that we have 2 radians here. A third radian would be just shy of halfway around the circle. And that should make sense with what the number pi is. Remember that pi is equal to 3.1415926535. And it goes on forever. It's an irrational, non-repeating decimal. So 3 radians should actually be just shy of 1/2 rotation around the circle. So the next logical thing that we want to do is we want to talk about the relationship between radians and degrees. We have 2 separate measures that we can use. We have radians and we have degrees. How do we convert between them? Well, it's very similar to converting between meters and feet or any sort of one-dimensional unit. So remember that pi is 1/2 revolution. Similarly, 180 degrees is 1/2 of a revolution. So we can say that these two angle measures are going to be equal. So we can say then that pi radians is equal to 180 degrees. Okay, so we actually have a starting point now. So now what if I wanted to know how much 1 radian was in degrees? Well, I just divide by pi. If I have pi radians here is equal to 180 degrees, if I divide by pi, then I have 1 radian. So I would have 1 radian is equal to 180 divided by pi degrees. Okay, what if I wanted to know how many radians a single degree was? Remember, a degree is defined as 1/360th of a revolution around the circle. So I could divide by 180 and I would have 1 degree is equal to pi divided by 180 radians. These are actually exactly the conversions that we use. And it should make sense because we stepped through it step by step. So if we wanted to convert from degrees to radians, we multiply by pi divided by 180 because I have 1 degree here is equal to this many radians. So if I have a certain number of degrees, I would want to multiply this by that certain number of degrees by that certain number, and it would be the same thing as multiplying this by the same number. We multiply by pi over 180. I'll do an example of these in a second. Similarly, to convert from radians to degrees, multiply by 180 over pi. Same idea. If I have a certain number of radians, and I want to convert that certain number to degrees, I could multiply this side by that certain number, and then I would have a certain number of radians is equal to a certain number times this number of degrees. Let's do an example to shore up what I was saying. Example here. Express 40 degrees in radians. So again, recall, keep in mind 1 degree is equal to pi divided by 180 radians. I want 40 degrees. That's how many degrees I have. This is 1 degree, so I need to multiply this side by 40. If I do that, I get 40 times 1 degree is going to equal 40 times pi divided by 180 radians. Which then means I have 40 degrees is equal to, if we cancel here, we get 2 over 9 times pi radians. This is how I'm going to do my conversions most of the time. And I want you to try one now. You're going to do the opposite. Express pi over 3 radians in degrees. Next topic I want to talk about is angles in standard position. Start with the definition of what standard position is. An angle is in standard position if it is drawn in the xy plane with its vertex at the origin and its initial side on the positive x-axis. So what that looks like is this. So suppose we have our xy plane here. This would be our x-axis and our y-axis like normal. Our initial side needs to be here on the positive x-axis. And then we rotate from there to our terminal side, which could be anywhere here. So this angle is said to be in standard position because its vertex is at the origin and the initial side is on the positive x-axis. Two angles in standard position are called coterminal if their terminal sides also coincide. Right, there's a couple of things here that are kind of quick and easy to miss with this definition. First, we're starting with the assumption that these two angles are in standard position already. It is possible to not have angles that are in standard position also be coterminal. But for the sake of the definition, we're going to assume that they're in standard position so that we can then figure out which angles are coterminal a little bit easier. So two angles are in standard position, meaning that their vertex is at the origin and their initial side is on the positive x-axis. We call these two angles coterminal if the terminal sides overlap as well. You might think to yourself, how do you get two angles with the terminals or with the initial side on the positive x-axis and their terminal sides being the same? How would they be coterminal? Wouldn't they just be the same angle? Well, not necessarily. So every angle is uniquely defined for one entire revolution. What I mean by that is if we start here, supposing we're starting in standard position, we start here, I can rotate all the way around and I would hit every single angle one time, exactly one time. I would hit every angle exactly one time. But what if I kept going? What if I went an entire revolution and then kept going to the next one? So if we have two angles, but instead of just going from here to here, what if instead we went from here to here and then all the way around again to be here, this angle here? These two angles are actually coterminal because their terminal sides coincide, they overlap. But the angles are actually different. They're not the same angle. This one is actually exactly 2 pi radians larger than this angle. And that's how we're going to figure out when two angles are coterminal. Now it should make sense why it's 2 pi radians larger, or 360 degrees larger. So think about it like this. We have this angle here. We'll call this angle T. And then we continue this angle to go in exactly one extra revolution. Now this revolution is 2 pi radians, or 360 degrees. That's going to be exactly what this angle is. So hopefully you can see why if we subtract two coterminal angles, we'll get some integer value of 2 pi or integer value of 360 degrees. We also don't necessarily need to add 2 pi. What if instead we subtracted 2 pi? Copy this again. So we have our t. What if we subtracted 2 pi? Another angle that's coterminal with this angle would be this. But notice that if we add these two angles together, call this angle S and this angle T, since they're coterminal, they generate one entire revolution, which again would be 2 pi radians or 360 degrees. So if we subtract these two, remembering that S is negative, we're rotating clockwise, not counterclockwise. So if we said T minus S, that would give us exactly 2 pi. Again, keeping in mind that S is already negative, so T minus a negative value will be T plus a value to give us the actual value of 2 pi. Adding this over, we get that T is equal to S plus 2 pi. And we could see that if we add 2 pi to the angle S, we would get T. So again, it's off by one full circle. Now, we could also do this where we go around any number of times, as long as we end in a coterminal position, meaning that the terminal side is the same, then they will be some number of circles apart. Let's go ahead and do an example. Find two coterminal angles for A, theta equals 2 pi over 3, and B, theta equals 13 pi over 4. I also want one positive angle and one negative angle. Let's go with A. Theta equals 2 pi over 3. I'm going to go ahead and draw that for you. We'll talk about these angles later. This is theta equals 2 pi over 3. So we have this angle. Now, if I want a coterminal angle, I want to rotate another certain measure of angle and land in the same spot. And to do that, I can add a full circle. Now, a full circle is just 2 pi radians or 360 degrees. But since we're in radians, we're going to stick with 2 pi. So if I wanted to find a coterminal angle, all I need to do is make an entire revolution, one full revolution. It could be 2 full revolutions or 3 full revolutions, but we're going to stick with one because it's easiest. So my coterminal angle, I'll call it theta star, is going to equal 2 pi over 3 plus 2 pi. The original angle plus one full circle. So we go the original angle and then one full circle. So we land in the same spot. Now 2 pi is the same thing as 6 pi over 3. So we get 2 pi over 3 plus 6 pi over 3, finding a common denominator between the two. And we end up with 8 pi over 3 as our final angle. So we can say then that 8 pi over 3 and 2 pi over 3 are coterminal. Suppose instead that I wanted a negative angle that's also coterminal. So I found a positive angle that's coterminal. I want to find a negative one as well. So I rotate again 2 pi over 3, but this time I'm going to go one full revolution in the opposite direction, in the negative direction, clockwise. So we rotate clockwise one full revolution. So we go 2 pi over 3 and then subtract 2 pi because that's one full revolution. So in this case, we would have theta star is equal to 2 pi over 3 minus 2 pi. And again, 2 pi is the same thing as 6 pi over 3, so we'd have 2 pi over 3 minus 6 pi over 3, finding a common denominator between these two, and we get negative 4 pi over 3. So I can say then that negative 4 pi over 3 is coterminal with 2 pi over 3. Now, remember also that 8 pi over 3 is also coterminal with 2 pi over 3. So does that mean that these two angles are also coterminal? Take a second and think about that. Coterminal just means that their terminal sides coincide. They have the same terminal side. So this angle has the same terminal side as this angle, and this angle has the same terminal side as this angle, so these two will also have the same terminal side, which means they are also coterminal. Do part B. Now our theta is 13 pi over 4. So let's find two coterminal angles, one positive, one negative, with 13 pi over 4. I'm going to draw that for you. You might not know exactly where it is. Okay. We'll learn about that, how to find them in a bit. Right here. This is 13 pi over 4. So again, in order to find a coterminal angle, assuming we don't know what the angle looks like, we can add 2 pi. We have 13 pi over 4 plus 2 pi. This will be 13 pi over 4 plus 8 pi over 4, which gives us 21 pi over 4. So we can say then that 21 pi over 4 is coterminal with 13 pi over 4. Now let's find the negative one. We do 13 pi over 4 minus 2 pi now. We're subtracting a full revolution, just like we did before. This is the same thing as 13 minus 8 pi over 4. Remembering that 2 pi over 4 is the same thing as 8 pi over 4. So we have 13 minus 8 will give us 5 pi over 4. Now, is this a negative angle? No. So we actually didn't need to add 2 pi to get a coterminal positive angle. We could have subtracted 2 pi as well and still gotten a positive angle, just because of how large 13 pi over 4 actually is. But it doesn't matter. We still need to find a negative. So we do now 5 pi over 4 because it's coterminal with 13 pi over 4, and we subtract 2 pi again. So from the original, we subtract 2 full circles now, and that will still give us a coterminal angle. So 5 pi over 4 minus 8 pi over 4 gives us negative 3 pi over 4. And this is a negative angle and coterminal with 13 pi over 4 because it's coterminal with 5 pi over 4. And 5 pi over 4 is coterminal with 13 pi over 4. Right, go ahead and try one now. Find two coterminal angles, one positive, one negative, with the angle theta equals 270 degrees. Next thing I want to talk about is the length of a circular arc. Recall, the circle of radius 1 is drawn with the vertex of an angle at the center, then the measure of the angle in radians is the length of the arc. Now, also recall that we actually extended this to be a circle of any radius. So if we have a circle, we have any radius here, r, then 1 radian around the circle would mean that we take this radius and we press it against the circle to go the distance that that radius is around the circle. Okay. So this distance would be r. This is still 1 radian. The measure, the angle measure, is 1 radian. But now this distance around the circle is r. It's 1 radius length. This is important when we're talking about the length of a circular arc, because what we're looking for is the length, this type of length, where we're going around a circle. So let's let S be the length of an arc. If we think about S as the length of a circular arc, we can say that we really only want a portion of the circle. And then we multiply that portion by the circumference of the circle to get the length of a circular arc. So S will equal the portion of the circle times the circumference of that circle. So if we only want, say, the length of half of the circle, that would be the portion, 1/2. We would take 1/2 of the circumference, and we would get the length of the top half of the circle. Suppose that we wanted only a quarter of the circle. Well, we would take 1/4, that would be our portion, multiply 1/4 times the circumference, and we would get the length of the arc from here to 90 degrees straight up. 1/4 of the circle. So now what we're going to do is we're going to extend this a bit. S will equal the proportion, which in this case, if we're talking about radians, because the radian measure of a full circle is 2 pi, we just need to find the angle that we want and divide it by that full radian measure. So if we wanted, say, 2 radians, that would be 2 divided by 2 pi, would give us the proportion of the circle that we want. So we'll have angle theta divided by 2 pi, keeping in mind theta is in radians. And we multiply this by the circumference of a circle. If you don't remember what the circumference of a circle is, it's exactly 2 pi r. So if we actually multiply these together, we end up with S is equal to theta r, because the 2 pi's cancel. Now, we also need this caveat. Theta must be in radians. All right, let's go ahead and formalize this. Length of a circular arc. In a circle of radius r, the length S of an arc that subtends the central angle of theta radians is S equals theta times r. Let's go ahead and do an example real quick. Find the length of the arc of a circle with radius 4 and central angle 120 degrees. Okay, so the first thing that we want to note is that our angle is in degrees. It's not in radians. So we need to convert that to radians first. How do we do that? Recall that 180 degrees is equal to pi radians, which means that 1 degree is equal to pi divided by 180 radians. Right, now we are looking for how many radians 120 degrees is. So if we multiply both sides by 120, we would have 120 degrees is equal to 120 times pi divided by 180 radians. Cancel what we can. 12 divided by 18, 2 over 3 pi radians is the same thing as 2 pi over 3 is the same as 120 degrees. So now I have my angle now in radians, 2 pi over 3. So now what I need to find is the length of the arc that subtends the angle in a circle of radius 4. So S will equal theta r. Now our r is 4. We have a circle of radius 4. And our theta needs to be in radians, so it's 2 pi over 3. So we end up with 2 pi over 3 times 4 is 8 pi over 3. Let me show you what this is. About 2 pi over 3. So here is the length. Here's the arc that we're actually trying to find, the length of the arc. We're trying to find this length here. We go from here to here, around a circle of radius 4, which means that this length is 4 units. This is 4 units as well. This length is actually 8 pi over 3 because we have a radius of 4. All right, the next topic I want to talk about is area of a circular sector. Recall, area of a circle is pi r squared, but following exactly what we did in the length of a circular arc, we're going to find the area of a circular sector. Now what that means is that if we have an angle like this, a central angle, we're trying to find the area of the shaded region here. It's a part of the circle, but it's only a part between the terminal and between the initial and terminal sides of the angle. Area of a circular sector is equal to the portion of the circle times the area of the circle. You can see that here. If I want to find the area of 1/4 of the circle, that would be 1/4 times the area of the whole circle. If I want half a circle, it'd be 1/2 times the area of the whole circle. Same idea. Now, as I said here, recalling that the area of a circle is pi r squared, we're going to write that here for our area. Now, the proportion, is very similar to how we did the length of a circular arc. That is going to be the angle that we go divided by the angle of the entire circle. Now again, it has to be in radians. So we do theta divided by 2 pi, where theta is in radians. So we end up with, when we multiply these two things together, the pi cancels, and we just have theta times r squared divided by 2. We have 1/2 r squared theta as the area of a circular sector. Let's go ahead and formalize this. In a circle with radius r, the area A of a sector with central angle theta, radians, is A equals 1/2 r squared theta. Let's do an example using this. Find the area of the given sector. Suppose that we have a circle, radius 6, and we're trying to find this shaded region. Further suppose that we don't know what that angle is, but we know what the opposite angle is. This angle here is 4 pi over 3. So how would we find the area of the shaded region? Well, it's still a circular sector, so we're still going to use A equals 1/2 r squared theta. Now theta is talking about this angle from here, this initial side, to this terminal side. We don't know what that angle is, so we need to figure out what it is. We know what the opposite angle is. We want to know what the blue angle is. Now, notice that the blue angle and the red angle make up a full circle. Let's call our angle theta, because that's the angle that we want to know. Now notice that theta and 4 pi over 3 make up a full circle. Full circle consists of 2 pi radians. So we would have then theta plus 4 pi over 3 is equal to 2 pi radians. So if I subtract my 4 pi over 3, I get theta is equal to 2 pi minus 4 pi over 3, which of course is 2 pi over 3. So we could say then that theta is equal to 2 pi over 3. And that's the theta that we want. We want this angle. So I know what my theta is. I need to figure out what my radius is. My radius is 6. It's given in the problem. So we would have A is equal to 1/2 times 6 squared times theta, 2 pi over 3. Cancel the 2. 6 squared is 36. 36 divided by 3 is 12. So we have 12 pi. 12 pi is the area of the shaded region. I want you to try one on the accompanying worksheet. Find the area of the circular sector with central angle 210 degrees and radius 4. Be careful. 210 degrees. This is important. Make sure that you understand the formula and what measure theta needs to be in. The next topic I want to talk about is going to be the circular motion. Linear speed is the rate at which distance traveled is changing. So if we have a point A and we have a point B, and we traveled this distance from point A to point B, then the speed at which we did that, or the rate at which we did that, is called the linear speed. Angular speed is the rate at which the central angle theta is changing. Now the central angle is theta. So as you move around, as you move from your starting point to your ending point, this angle theta is changing. The rate at which that angle is changing is called your angular speed. Linear speed and angular speed. Suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. Let s be the distance the point travels in time t. Then the speed of the object is given by, we have two speeds. The angular speed will be omega equals theta divided by t. You've traversed theta radians in time t, so theta divided by t is the angular speed, and linear speed. This one is good old-fashioned v is equal to s over t. Now s represents the distance that you actually traveled. So let me show you what we're talking about here. We have a circle, and we have a point on the edge of this circle, and it's running around the circle. Here, like that. So we draw a ray from the center of the circle to the start point and to the end point. The angular speed will be the change in this theta, this angle, as he rotates around the circle, and then comes to a stop here. So we take that angle that he traversed and divide it by t, how much time it took him to traverse that angle. Now the linear speed is a little bit different. It's actually this length here. It's this actual length. As if you're picture yourself running around the edge of a circular track, like a track and field track, but a circular one. you actually are running this distance, and the speed at which you run that distance is your linear speed. Now, I do want to note that these two are actually related, and we're going to get into that in a bit, but I want to do an example first. An Ewok is rotating a stone in a 1/2 meter long sling 12 revolutions every 5 seconds. Find the linear and angular velocities of the stone. We have a circle, and our sling is 1/2 meters. And in this sling is a stone. Now this stone is rotating 12 full revolutions every 5 seconds. We need to figure out what the angular and linear velocities of this stone are. So the angular velocity will be omega equals theta divided by t. How many radians divided by how long it takes. But we have 12 full revolutions. How many radians is that? 12 revolutions, each being 2 pi radians, is the total number of radians that we have. So this will be 24 pi radians. That's theta. Now t is 5 seconds. 12 revolutions every 5 seconds. So we have t is equal to 5. So we end up with omega is equal to 24 pi divided by 5. Now the linear velocity, on the other hand, is v is equal to s over t. Now we need to figure out what s is. Remember, s is this distance. It's exactly the arc length of 12 full revolutions. Now we have a 1/2 meter long sling, and we have the number of revolutions, also the number of radians, because 12 revolutions is 24 pi radians, as we found out in the angular speed part of this problem. Remember that s is equal to theta times r, where theta is in radians, not degrees. You know, 12 revolutions is 24 radians, so theta will be 24 pi. R is going to be 1/2 because we have a 1/2 meter long sling. That's our radius. So s will be 12 pi. And then t, of course, is still 5 seconds. The stone moves 12 revolutions in 5 seconds. So v will equal 12 pi divided by 5. That's how fast the stone is traveling. So now what I want to do is I want to talk about the relationship between the linear and angular speed. In that last example, we should have seen at least a part of it. You might not have noticed it, but recall. The length of a circular arc is s is equal to r theta. Linear speed is equal to v equals s over t. And angular speed is omega equals theta over t. Noting that s is equal to r theta, we can relate our s and our theta here, which means we could relate our omega and our v. So s, if we replace this with r theta, we get r theta over t. Also notice that omega is exactly theta over t. So if we move this r off the numerator and move it in front of the fraction, we would have then r times theta divided by t. Now theta over t again is exactly omega, so v is equal to omega r. Okay, let's formalize this really quickly, and then we'll do an example. Relationship between linear and angular speed. If a point moves along a circle of radius r with angular speed omega, then its linear speed v is given by v equals omega r. Now what we're saying is the linear speed of an object is the same thing as the angular speed of that same object times the radius of the circle. Try one on the accompanying worksheet. Stormtrooper runs along the outer edge of the Death Star 4 kilometers from one battle station to the next in 30 minutes. Find his linear speed. If the radius of the Death Star is 80 kilometers, find his angular speed. That's going to be it for today. I will see you all in the next lecture.